Good evening, everyone, and welcome to the 2025 Townsend Lecture. My name is Kareem Jaffer. I'm the Public Events Coordinator for the RASC Montreal Center. Dr. Dang will be our speaker, but I'm going to introduce her in a little bit. We've got a few things that we just want to go through before we start. And as always in the RASC Montreal Center, we try to start with a land acknowledgement, but also a land and sky acknowledgement. Because we are on the unceded Indigenous lands of both the Kahnawake as well as the Anishinaabe, but we also share the night sky with not just the First Nations and the Indigenous and Métis people, but with the ancient cultures and peoples all over the world. And we often see that when we talk about the moon. And as many of you know, we are actually currently at a waxing moon. And last month, earlier in September, would normally be our harvest moon. It would be the moon that we would talk about as our autumn moon, when the nights would be open, sky would be up for a very long time. The full moon would almost not seem to change for 3-4 days in a row, while we had the 12 hours daylight, 12 hours night, so that the farmers could work well into the night. But this was an unusual year because we actually had 13 lunar months from spring to spring. So last month, this previous moon was referred to by most First Nations as the halfway moon. And now we pick up with the harvest moon at the moment, or the mate calling moon, or the moose antlers ruffling moon, depending on which First Nations you look at from across Canada from coast to coast. They all talk about the moons in terms of the way they connect with nature and what you see in nature at the time. And a couple of years ago, there was a beautiful video that came out from the Quebec government to celebrate all the First Nations that we have here within Quebec. So we'll take a moment to watch this video.
I am here. Can you see me? We both live here. But do you really know who I am? Who we are? We are 11 different nations, 11 languages, expressing identity and territory. Each sharing our strength and our story. We carry seasons, gestures, and culture for today and for our future. We are 11 nations, 11 ways of living here.
Wendat,
Iyo, Kanyaga, Mi'kmaq, Abenaki,
Warastahui, Inu,
Medikmak,
Anishinaabe,
Naskapi. Now you see us, and that's a start.
Now, before we actually talk about the RASC and what the RASC Montreal are, we're lucky to have with us today, live from Arizona, our honorary president, David Levy. Now, David Levy, some of you may know the name. He is a world famous comet hunter, the Shoemaker Levy 9 that collided with Jupiter back in '94. He was one of the co-discoverers. And we are really lucky ever since COVID began that our weekly meetings, that whenever we have them on Zoom, but especially our public events, David is able to join us from Arizona and give a literary reference and a welcome. So David, pass it over to you.
Thank you so much, and I'm so glad that the internet so far is working. The Townsend Lecture is so dramatic and so exciting that I need to begin by saying a few things about it. C. Horley Townsend died in 1954. He left a bequest to the Montreal Center for $25,000. That was in 1954, so you can imagine what that would have been now. And it was decided at that point to use the money to start the Townsend Lecture. And we'll be introducing Dr. Lisa soon. But in the meantime, it has quite a personal relationship with me. I did not go to the 1972 lecture because I was unwell at the time, but Constantine, I think we all remember him, very strongly recommended that I go, well or not, because the lecture that year was Carl Sagan. And we've had some amazing lectures. In 1964 was the first one I attended. It was Gerald Clemens. And he gave a very good lecture, except he didn't know how to pronounce galaxy. He kept on calling it galaxy. And to this day, I don't understand why he did that. In 1994, I believe I was the Townsend lecturer, and I talked about one of the comets that I discovered. Tonight, we're going to have Dr. Lisa, who is going to give us a lecture that I am very excited to be part of, and as long as my internet stays up, I'll be able to attend. And I'd like to go a little bit to my favorite writer, William Shakespeare, by far my favorite writer. My mom kept on saying that I don't tend to finish what I start. And I got my undergraduate degree in English literature at Acadia. I got my master's degree at Queen's University in Canada. But then I decided I didn't want to go any further. And for a long time, then came a series of comet discoveries, Shoemaker leaving 9, then my marriage with Wendy. And a couple of years later, I walked into where Wendy was talking, and I said, Wendy, sweetie, I just got this terrible idea that I should finish what I started, as Mom always said, and get my doctorate. But don't worry about it. I'm going to stomp on that idea. And I won't have to worry about it for another 5 years. And Wendy looked at me and said, David, before you start stomping, I think in this case, your mom is right. And before that conversation was over, I had applied to the Hebrew University in Israel, got accepted there. And I think Mom would have been happy that I did finally finish what I was going to do. I know Dad would have been, because when I was in high school, I was talking with him in the vestibule of our home, and I believe I was on my way to the meeting of the Montreal Center. And anyway, he looked at me and he said, shook his head and he said, if you don't inherit my love of Shakespeare, I may disinherit you. And I looked at Dad and I said, Dad, I am really promising you that I'm not going to not inherit it. And Dad started laughing. And he said, you know, I'm joking, right? And I think Dad would have been pleased that I took that love as far as I did. And now we get to the quotation. It's my favorite Shakespeare quotation. I've done it here before, but I'm going to do it now. And it has to do when this is in his final fight. It's in Act 5. And he's in his final fight. He's about to start his final fight with Macbeth. And he gets the news that his wife, Lady Macbeth, has died. And at that moment, he just gives up. He wants to die. He doesn't care how he dies, but he's lived long enough, and he just wants to be done with it. And right at that point, I'm thinking, Shakespeare sitting in his study with his laptop and his internet connection, which is probably better than what we have now. And he's saying, now, what am I going to write? What is Macbeth going to say? And I like to imagine that there's a pounding, a gentle tapping on his shoulder at the time. And he turns around in his study, and he finds that who's tapping on his shoulder is God. And God looks at him and says, Will, take a break. Take your email, play video games, go out and buy a new keyboard, have some fun. I got this. And the speech that follows is, in my opinion, nothing short of amazing. For the simple reason that as he was writing it, without even being aware of it, Shakespeare anticipated by over 300 years Einstein's general theory of relativity. And I'm sure there are a lot of you in the audience right now that are saying, oh, no, he didn't. I can argue that the next time I come to Montreal, it'll be definitely next summer, maybe earlier. But anyway, I believe that he, without even being aware of it, that he had in mind the idea of general relativity. And to honor that, I'm going to add just 2 words in the quotation. And here it is. She should have died hereafter. There would have been a time for such a word. Tomorrow, and tomorrow, and tomorrow. Creeps in its petty pace from day to day to the last syllable of recorded time, then is heard no more. Out, out, brief candle. Life's but a walking shadow. A poor player that struts and frets his hour across the stage, then is heard no more. It is a tale told by an idiot, full of sound and fury, signifying nothing, signifying everything. Kareem, bless you, back to you. Thank you. Thank you.
Thank you so much, David. We're happy that you're here with us, and don't go too far because you know there's going to be something else I'm going to call on you for in a few moments. The RASC is the Montreal Center is one of 30 centers across the entire country. And we are the largest amateur society kind of honoring this passion here in Canada. And our centers are all active, not just in members, events, and pursuing the hobby of astronomy and some of the science of astronomy, but also the outreach and education side, which is what tonight and a lot of the events that we do here at the Montreal Center are all about. One of the big things that we do on the member side is observing programs. And our observing programs that we have here at the Montreal Center are not just the national ones, which you see lined up here at the bottom. And we've had some of our members recently get the Observe the Moon or the Explore the Universe certificate, and we will be honoring a few of those during our annual general meeting to come. We have a special one here in Montreal, which is our Double Star certificate, and it was the first one of its kind here in Canada. And so I have here one of the quotes from the Double Star certificate, but while Santiago comes up to honor one of our members with a bronze level certificate, I'm going to ask David to just mention briefly about the onset of this Double Star and our dear departed friend, Carl.
Thank you. 1964, I was visiting the center, and there was another young person who was there, and Miss Isabel Williamson, who was in charge of the observing program at the time, introduced me, and we became close friends. We became extremely close friends when, in 1967, I was very nearly expelled from the facility after getting into an argument with Miss Williamson. And I regret that to this day. And I remember my father yelling at me about it for being so immature, and then taking it all back a couple of weeks later. And he said, "You were provoked and it was okay." And I said, "Dad, you were right. I do have a lot of growing up to do." And Dad looked at me and he cried a little bit and he said, "You just understand." And I've never forgotten those words. And Carl and I kept on the friendship. It lasted through high school. It lasted for decades while he was working at McGill, in the Foster Radiation Lab. And it lasted for even more decades as he was running Double Star section of the center. And I remember I have another good friend named Tom Meyer. I need to get in touch with again. He lives in Toronto right now. And we were talking about Carl and his double stars. And I said, double stars are very important. And Tom said, yes, to him. But not just to him. They're very important. There's Dawes in England, and he really started the theme of double stars in binary systems. And he also, I believe, was one of the people who knew Alfred Lord Tennyson. And Tennyson himself was an amateur astronomer with a telescope, but was allowed to use a great telescope in London that Dawes was using for his double stars. He took advantage of that a lot. Carl and I talked about double stars over and over again. Anywhere from the Vireo, which I think all of us in this room have seen, to the companion of Sirius, which I have seen. We even got a little certificate from Carl about that. And then one day, maybe about 4 or 5 years ago, I get a phone call from Carl's family. Carl got COVID and passed away almost very suddenly within a couple of days of getting it. I miss Carl. He's one of my dearest and closest friends. He was alive and well when I lost my spouse, Wendy, 2 years ago. We talked about that. And he visited my mom many times. And we just had this very long friendship. And I wanted to say that Carl's love of double stars is something that we at the Montreal Center are continuing today. And it's I think we may be the only center in the society, and one of the only ones in the United States as well, that has a dedicated double star observing section. I would encourage all of you to find out about it. If you're not members, to join our center, become part of the family, and enjoy Carl Jorgensen and his lovely and wonderful double stars. Thank you. Thank you.
Townsend Lopez is our observational activities director, and I'll say a few words about the observing program.
So we do a lot of observing programs. The double star is just one of them. So if you're interested in doing any one of these observing programs, it's basically a list of objects that you'll go around and try and observe at your own pace. And you can start whenever and finish whenever and submit your results to myself or Nicole. And we're doing these things for various people who have jumped into this adventure and observed the night sky and discovered all these objects for themselves. So whenever you want to, just go ahead and jump in. And for tonight, we have Nicole has completed one of these. It's the double stars. As you can see, there hasn't been a whole lot of people who have jumped in and succeeded to complete them all. You started, as Toby mentioned, by Carl Jorgensen, who's right up there. And Nicole has achieved the bronze, which is the observing 100 out of 300 known, well, double stars on our list of observable double stars. It's not a extremely difficult thing, but it requires a certain amount of, you gotta start it, you gotta finish it. So as you can see, since only a few people have actually done it, it's an achievement to behold. So congratulations, Nicole. Our certificate, we didn't actually print it, so we'll hand it over at the annual general meeting. It's just a trick to get you all to come back.
Thank you, Santiago. And for those of you that were here at some of our earlier meetings, we actually talked about trying as a society to have a good number of different beginner level certificates finished by the end of the year. We are at September 27th. There's still more than enough time for people who are interested to work on the Explore the Moon or the Explore the Universe, or people like me who've done the observations and just haven't gotten around to writing them all down the right way so that we can submit them. Santiago and Nicole are the ones that review them, and you can pass them any of these certificate programs. There's some that are actually open to non-members as well, right, Nicole? Explore the Universe, yeah. Right, which allows you to just look for very specific objects in the night sky. And if you come out to our event, on, for example, next Saturday when we have the International Observe the Moon Night, we'll help you. We'll help you figure out what it is that you're looking at in the night sky. And it gives you a chance to really start to feel like you know the night sky, that it's a friend when you go out there. Now, our Montreal Center, you can kind of get the idea that we're pretty active. We have events almost twice a week. We have our members' clubhouses at the Arboretum here. We have a dark sky site near the US border. We have another dark sky location we go to just off island to the west. We have a astronomy library here at John Abbott College where we hold monthly events through the winter, through the bad weather times. And then we have these monthly public events. We have our newsletter, which is now going out to members of the RASC across the entire country, since there's no more National Astronomy Magazine in Canada. Our Montreal Center one actually has that reach. And so for the students that are here, if any of you have ideas of articles you want to write, you can submit them to the RASC Montreal Skyward and be published in a local and national reach newsletter. In terms of our upcoming members events, we have a couple of dark sky outings next month. We have clubhouses on 3 of the Wednesdays. And then the 4th Wednesday, it's actually a nice, almost no moon night, and it's near the peak of the Orionids. So it's a members clubhouse at the Arboretum, but we're going to extend an invitation to the Dawson Astronomical Society and the John Abbott College Space Club to join us out there for a meteor shower night. And if the weather's not good, we'll have a talk indoors instead. We have a citizen science workshop that's coming up for members, for students, and we're going to have some of the local clubs that are interested in getting into citizen science join us, because it's a way for, no matter your background, you get a chance to participate in science. And this particular one will focus on images from a space telescope we might hear a little something about today, the James Webb Space Telescope. We have library nights coming up in the winter time in November, December to begin with. We have a movie night coming up on November 15th, and our movie nights are epic. David Schumann will talk to you about them afterwards over coffee if you have questions. And then we have our annual general meeting on November 22nd. Now, before we get to the upcoming public events and the main event tonight, we've got one more thing, which many of you will be interested in. A couple of years ago, Russell Freilich, who was our outreach coordinator at the time, he and myself were working with the national team on revising a introductory astronomy course for the general public. And we ran a first session of 6, and then Nader took over as outreach coordinator and ran the second section of 6. And now he's put together a revisiting of the first section of 6. Nader?
Well, thank you, Kareem. I'm just going to take another minute of your time before the lecture and the highlight of the evening. The NOVA program stands for the New Observers in Visual Astronomy, and it's designed for the very beginners who just dipping their toes in the night sky and observation and astronomy and all that. It is designed to multiple 2-hour sessions. We're starting our 3rd consecutive year of NOVA here at John Abbott College I.K. Wilson Library. It's going to be running from November 7th to December 12th, or 6 Fridays, consecutive Fridays. And it will cover topics such as orienting yourself in the night sky, finding constellations, asterisms, and objects in the night sky, as well as getting acquainted or even mastering the use of your equipment, whether it is a pair of binoculars or a telescope. You don't have to have any knowledge at all. So if you are interested in starting the observation program, such as you observe the universe, which is for non-members as well as members, or if you are a member and want to look for all of these double stars and you don't know where to look, then the NOVA program would be the first step you can take into orienting yourself, finding the double stars, completing one of these programs, or just be out there and observing at your own leisure. So if you are interested, or you know somebody is interested, send me an email at outreach@rascmontreal.org. Or if you have any questions, just find me after the lecture. I'll be around at the table or somewhere, and I'll be more than happy to answer your questions. Thank you.
Thanks, Nader. So our upcoming public events, so you saved the date. Next Saturday, we are at the Borgen Arboretum, and it's an incredible event. We will have music, we will have poetry, we will have a live hands-on art activity to work on constellations and working out your own story of the stars. And we will have observing of the moon with a moon talk by Nicole. If weather is good, we'll actually be out there with our large 14-inch telescope open as well. And then at the end of October, on October 29th, our John Abbott College Space Club will be hosting spooky nights right here for kids and for kids of all ages. And it's from 6 to 8 on a Wednesday so that it doesn't interfere with any of your Halloween plans. But it gives you a chance to come out and do some space-themed activities or to come and actually help out and spend some time with the John Abbott College space students. Now, for the Townsend lecture, Joby gave you a little bit of the history. This lecture has been one of our keystones for decades. We are well into the 7th decade of these incredible lectures. And it began with the very first lecture by Dr. Harlow Shapley. Now, in the past years, we've been focusing a little bit more on some of the incredible astronomy and space exploration science done here in the Montreal area. During our centennial year, we had the Constellation mission manager, Steve Iris, come in. And then we had the Canadian Space Agency outreach scientist for the James Webb Space Telescope, which we're going to hear about today a little bit, some of the results from it. Natalie Willett was here. And we've had a lot of incredible speakers from the Institute for Research on Exoplanets, including Natalie, and Lisa was there just recently. We've had Jason Rowe from Bishop speak. We've had Emily Lafleche, one of our graduates, come to us live from a moon base in Poland. And another one of our RASC Montreal friends, Shaziana Kadarli, is there right now in Poland at the moon simulation base, and will talk to us next year about her experiences. We had Andrew Higgins talk to us about interstellar propulsion. And since then, our center has been working on research with Andrew along these lines and along the astronomy line. And then last year, we had Jonathan Gagne speak to us about some of the incredible work done with the Gaia satellites database. And so we're really privileged tonight to have with us Dr. Lisa Dang, who recently finished here at University of Montreal and has a professorship started at University of Waterloo. And I've followed Lisa's career for a few years. And then when she was one of the first students whose project was chosen for the first batch of work done on the James Webb Space Telescope, we had two students in the Montreal area, including Lisa, get their project design and their research papers and research direction approved to have time on that telescope. My jaw dropped. And I was talking to Natalie, I'm like, I need to get Lisa to come speak. I need to get Lisa to come design. Anytime she's doing research, don't talk to her. Because she knew that if I talk to her and I ever come out here, it's not going to stop with like one talk, right? Because you'll see there, we've got Fizza Info, one of our students in Ontario who has connected with me through one of my other RASC education public outreach people. I already sent Fizza's paper to Lisa to look at and, to try to connect her for a bit of a discussion. This summer, we had Kevin come in and speak with Lisa a little bit and then work with her. So rather than me trying to summarize a few things, I'm going to ask Kevin to be the one to introduce Lisa on behalf of the student. Kevin?
Good evening, everyone. I'm Kevin Chen, and I'm a second-year science student. So, Lisa, I'm going to give a brief introduction about Lisa. Lisa did her PhD degree at University of McGill at 2022. After that, she did her postdoc in University of Montreal. Then she was currently working at University of Waterloo. And this summer, I was honored and lucky enough to work with Lisa. Mr. Jaffer introduced me to Lisa, and me and Lisa look at the wind speed on the exoplanets. And Lisa had deep understanding in exoplanet, and it really benefited me a lot in my studying and helped me a lot go through my projects. Yeah, and hope you guys enjoyed the presentation tonight, and hope you guys have a good evening. Thank you.
Thank you, and Kareem, for the wonderful introduction. And I just wanted to highlight that it was a pleasure to work with you over the summer, Kevin. I hope you had as much fun as I did orchestrating different students, including you. And I hope that you also had a great observing time at Montreal as well. So before we start, I'm just going to do some Zoom magic and change the slides so that you can all see my slides. but that always requires a little bit of technical difficulty before we set off.
You practice that.
That was smooth.
They call technical support.
Okay, so we can get started. Yeah, so as Kevin said, I did my PhD here at McGill, and then I went to the University of Montreal. I actually grew up here, so I was born and raised up here in the northern part of Montreal in Saint Michel. And then later on, I went to Dawson, so I see that there's a Dawson crew over here. If Nadim is still there, you can let him know that I think taking the astrophysics course with him was one thing that set me off on the trajectory today. But anyhow, so today, thank you all for coming tonight. I'm here to talk about lava planets, but a little bit before I dig into this, so I heard that if weather permits, we might have some observing after this, but then earlier today, I think I was very optimistic because the sky was very clear. So just a quick question. What do you think astronomers are really enthusiastic about?
Astronomy.
Astronomy, that's a good one. Another one is a clear sky. And what are we hoping for tonight? A clear sky. A clear sky, exactly. But what is our biggest obstacle to being able to see the night sky tonight?
Montreal.
So it's the exact same thing that prevents us from seeing anything cool in the sky, including a solar eclipse, auroras, or even an alien invasion. But unfortunately, we all know that the southern magma is not conducive for perpetual sky seeing. And the atmosphere is really what I want to focus on over here. So the atmosphere is great, but its ability to condense into clouds sometimes makes it very difficult to see what's happening in the sky. And so because the atmosphere is one of our biggest challenges to get great observations, this is the reason why we like to put our telescope on top of mountains or on top of some of the highest mountains. This is to minimize the amount of atmosphere that you have on top. And so sometimes the clouds will form below these telescopes, which is great. However, when you're trying to study, like I do, the climate and the atmosphere of other planets, it's really important that you find some way to not kind of like blend the signals that we have from our own atmosphere. So this is why on top of putting telescope on mountains, we sometimes also put them in space. And so putting telescope in space, they're just essentially a satellite that instead of pointing towards Earth, they're just pointing at other stars. But there's two reasons why they're so great. One of them is that they're not rotating with the Earth, and so there's no daytime. They can basically observe 24/7 if they wanted to. And then the other thing is that there's no atmosphere above, and so you have a lot more stability for these telescopes, which is something that we really need in the type of science that I do. So another kind of cool idea, I don't know if it's a cool idea, but one way of being able to always look at the sky and not having to fly into the sky to do so is, what if the Earth didn't have an atmosphere? So this is a picture that I pulled out. So imagine if we were living in a world where there was no atmosphere and no light pollution. Then you would be able to see the beautiful night sky every night. How wonderful is that? But I'm here to argue that a world without an atmosphere, although all of the night skies will be beautiful, it's kind of a boring one. And the reason why is, so if you don't have an atmosphere, you can see the night sky, but a world without an atmosphere is also a world without meteor showers, because you don't have an atmosphere to interact with the meteors when they hit the atmosphere, so you wouldn't be able to see these trails over here. But it also means that you would have a world without colorful sunsets and sunrises, which is one of my favorite things to look at. Actually, it's one of my favorite skies to look at, but don't tell the other astronomers. We also wouldn't have these beautiful, so sometimes when you see the moon rising near the horizon, they kind of look big and distorted and reddish. I also think that these are beautiful, but we wouldn't have them if we didn't have our atmosphere. And then finally, it would be a world without rainbows. Also one of my favorite things. So, as someone who studies exoplanets, so I'm an astronomer who studies exoplanets. I'm interested in studying planets that are orbiting other stars than our sun, so outside of our solar system. And that means that there's a sharp contrast between my colleagues, astrophysicists, and I. So while my colleagues are looking up at the night sky and they're getting these beautiful images of the night sky, sometimes at very large scale, and they're trying to solve big mysteries of the universe, going back to a cosmological time, so near the beginning of the universe, I do something that's slightly different. So my observing strategy is, I haven't timed this, so this might be long, but instead of looking at the entire sky, I like to pick one star, and then I zoom in, 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 up until, anyways, at some point the video is gonna stop on a single star. But you can see here is all of the pictures that I like to take of the sky are not these large scale pictures where you see large galaxies and nebulae, but rather you really, really focus on one star at a time. Okay, so this video is a little long, but at some point we will be focused. And yeah, okay. But once you focus for enough, one thing that you notice here is that you see that this star is kind of like blipping. The brightness of the star is kind of like blinking at you. And the reason for this is because some of these stars have planets that are orbiting around the star. And when they pass in front, they kind of block a little bit of the area of the star and kind of like makes the star a little bit dimmer, momentarily. So this is what I'm interested in. I like to zoom in one star at a time and then carefully and intimately look at each individual planet to see what can we tell about them. And more particularly, I like to ask myself, if we were to live on this planet, what would the sky look like? So, would there be any sunsets? Would there be any moonrise? And if there are, what would they look like? And then finally, is there any rainbows on these planets? And so in order to answer these, there are some, we can now use some powerful telescope like the James Webb Space Telescope to get signals that can tell us something about the atmosphere of these planets. Okay, so essentially what we're looking at is we're looking for signals that tells us that there is light from outer space that is interacting with the atmosphere of these planets. And so before I dig into exoplanets, I'm just gonna give a couple of examples of interactions of light from outer space with the atmosphere of the Earth and explain why we have sunsets, why we have these weird moonrise, and then also particularly why we have rainbows. Okay, so the reason is, and I think this is wonderful, is light is what we call chromatic in nature. So when you look at white light, it's not just a single color that you're seeing multiple light of different colors that are kind of like blended in. And so one way of illustrating this is normally if you see a ray of sunlight, which is white yellowish, you can put it through a prism and that will separate each individual light of different wavelength and allow you to see basically all of the different colors that this light contains. So sometimes you see something that looks like a rainbow, but it extends much farther than the rainbows that we can see with our eyes. So you can go down in the ultraviolet and up in the infrared. But this is not something that we can see, but we can build telescope to be able to detect. Okay, so colorful sunsets and sunrise. So why does it happen on Earth? Okay, so basically these are just 3 examples, and you can see here by how colorful they are. These essentially reveal the chromatic nature of light and allows us to understand what's happening in the atmosphere and why the atmosphere does this. So let's start with these colorful sunsets. So why don't we see these colorful, beautiful colors at all times during the day? We only see them at sunsets or sunrise, and the reason is because the atmosphere on the Earth has the ability of what we call scattering light. But it doesn't scatter all lights equally. It scatters different colors of light depending on how thick the atmosphere is or how dense the atmosphere is. So for example, during daytime, the rays of the sun doesn't really hit near, or when you're an observer on Earth, during the day, but what you see is the light of the sun hitting the upper part of the atmosphere. So essentially, these like upper parts of the atmosphere are a little thinner, and they're very efficient at scattering blue light. And so this is why our sky is blue, for example. But when you're at sunset, and you can see it from the little man that is standing over here, is that the light has to go through a denser part of the atmosphere. And when the atmosphere is denser, it has the ability of scattering red light a lot better. And so this is why at sunset, you see these redder shades in the sky. And we sort of know this because we've also looked at sunsets on other planets. So this is a picture of what a sunset on Mars looks like. And the reason why the sunset is blue is because the air or the atmosphere on Mars is much thinner than the Earth. So about 100 times thinner than the atmosphere of the Earth. So essentially, it never gets dense enough to have this efficient scattering of red light. And this is why all the sunsets on Mars are always bluish. Okay, so essentially, if we were to ask ourselves the same questions for atmospheres on exoplanets, then in order to understand what sunsets would look like on these other worlds, we would have to know how thick and dense the atmosphere is. And one way of figuring this out is also to have a sense of how strong gravity is on these planets. Okay, so next, the next question that I have is how distorted can moonrise or any body rises by the horizon can look like on other planets. And so let's talk about why this is happening. So just as an example, this is what the moon looks like when it's well above the horizon over here. And you can see that not only is it white-ish, but it's also not distorted inside. And so the reason that this is happening is because of atmospheric refraction. So essentially, when you're looking at something through another medium, what you're looking at can look distorted. And so this is the same concept that you can see happening on this pen that is in this glass of water. So essentially, the pen looks kind of straight and not distorted, but once it hits or it goes through another medium, it gets distorted. And then not only is it not at the right location, but it's also not the right size. And so essentially, same thing is happening when you're looking at a moonrise, for example. So as the light coming from the moon goes through the atmosphere, it goes through different layers of the atmosphere that have different density. And that has the ability of not only distorting the actual position of where the object is, but also distorting the shape of the moon. And there's also another thing that's very important here. It's not only, so you normally don't see something distorted when it's right above you. It really has to come at an angle in order for you to see this distortion. So this is why we only see them by the horizon when they're about to rise or sun or set. So in order to understand how objects might be distorted on other planets, it's really useful, or the one thing that we need to know is what the composition of the atmosphere is, and again, what the density is. So the density is not just set by the gravity on the planet, but it's also set by what kind of molecules do you have? Are they heavy molecules, or is it very, very light hydrogen? And both of these are going to tell us something about the index of refraction on these atmospheres. And then finally, rainbows. So rainbows only happens on Earth because the atmosphere of Earth has the ability of condensing into droplets of water. And so when you have lights from the sun kind of like hitting these water droplets, there's two things that are happening. So the same refraction that I talked about earlier through the atmosphere is happening within each droplet of water. And then in addition to this, you also, because of the difference between the droplets and the air that is surrounding the droplet, we also have reflection within the droplets that is further scattering and refracting the light. And so this is why we start to see the individual colors kind of like separating. And this is what gives rise to these beautiful rainbows over here. And if you look carefully here, there's not only one rainbow, there's multiple rainbows on these images over here. And so this happens when you have multiple reflections within a single water droplet. But in case you didn't know, these type of rainbows are not the only types of rainbows that happen on Earth. Oops. So sometimes we have these things that are called fog bow. So you don't need a lot of rain to have this. Sometimes you can have fog. Fog is essentially also water droplets that are much smaller in size. And so this is why if you ever see one of these fog bow, they're not these like large rainbows that you see in the sky. They're rather these like small concentrated rainbows. And then another one, this is a personal favorite. I've never seen this before until last year. But one night I was walking outside, and then I looked up at the sky and I was like, this kind of looks like a rainbow, but I've never seen a rainbow at night. So does anybody in the audience have a clue as to what's happening here? Why can we see a rainbow at night? Is that a
All the moon balls, I'm going to guess that is the light from the moon refracted within water droplets.
Exactly. So the reason is in the name. So essentially at night you can also have rainbows. So basically these are fairly rare and you need special conditions to see them. So not only you need to have had a recent rain, so a lot of water droplets in the atmosphere, but you also need a lot of light scattering from the moon. So oftentimes you have the most chance of seeing this during a full moon, where you have the maximum amount of light. But you also need a little bit of opening within the clouds in order for these moonlight to go through the atmosphere for you to see this. Anyways, whenever there's a full moon and you're like, oh darn, I can't look at the sky because the sky is too bright now. This is a perfect opportunity, especially if it's cloudy and rainy, to go out and look for moonbows. Okay, so in order to figure out whether or not rainbows are possible on planets, there's a few things that we need to understand here. One of them is, what is the temperature of this atmosphere? Is it a right temperature and a right pressure for droplets to condensate? And then the other one is you also need to know the composition. So what kind of droplets are you going to get? And this is like going into details here, but another component that you need is the right amount of difference between the background gas that you have, so the gas that is mainly making the atmosphere, and the droplet itself. So these are all special properties that the Earth has, and we just don't know yet whether any of the atmosphere of these other thousands of exoplanets that we found do have. But I think that now that we have a special ability of studying the atmosphere of exoplanets, perhaps we can start answering some of these questions or getting close to some of these questions. Okay, so now let's jump into the topic of tonight. So the talk tonight is called Hellish Planets. And this is because over the past 3 decades, astronomers have been really good at detecting planets. And in fact, they've discovered such a large diversity of exoplanets that we can now ask these questions for a bunch of different trial cases. But the one I'm going to talk about today are lava planets. So my question tonight is, why don't we ask ourselves what the sky looked like on worlds that look like this? So absolutely not habitable here, but still very interesting, and I hope that I'll convince you of why. So hellish exoplanet skies. So we're asking ourselves what sunsets look like, whether or not there are moonrise, and if there are they distorted and by how much? And then finally, can hellish planets have rainbows? Okay, so the roadmap for tonight, I'm first going to talk about how we found these hellish planets. How we can measure their mass and have a sense of the gravity for these planets. And at the end, how can we detect the atmosphere on these lava planets? And then finally, can we tell something about the lava? So to begin with, I'm first gonna backtrack a little bit and ask and remind yourselves, what is a planet? So according to the International Astronomical Union, a planet is a body that is in orbit around the sun, that is massive enough to be round and has also cleared its entire orbits of all the debris that is in the way. And so this is the reason why Pluto, a couple of years ago, was demoted of its title of a planet. It is now a dwarf planet because it hasn't fully cleared its orbit. So for a very, very long time, the only planets that we had known in the universe were the planets of the solar system. So essentially, all of the theories that we had about how do planets form and how do they evolve were only based on these 9 plus or minus 1 planets over here, or data points that we had over here. And then we had about a century to think about how of a theory that would fit what we observe now in the solar system. So we used to think that the reason why the solar system architecture is this way, so you have the gas giants that are very far away from the sun, and then closer to the sun, you have these terrestrial bodies. So these like smaller, compact rocks that doesn't seem to have that big of an envelope of gas. Okay, so because we sort of knew, or for a long time, the only evidence for planets that we have were the ones in the solar system, people started thinking the sun is just an average an average star. So if you put our sun in context over here, 10% of all of the stars in the Milky Way are just like the sun. And then there are 20 billion stars in our galaxy here. So surely we must not be the only star that has planets around it. So because the sun is a very average star, it's sort of like very in the middle of the biggest and the smallest stars in the Milky Way. A lot of the focus at the beginning were to target stars that look like the sun to see whether or not there were any exoplanets that orbited around them. And so it all started with 51 Pegasus B. And if you didn't hear, so in 1995 or so that was not too long after I was born, and maybe way earlier than some of you were born. But in 1995, or a little bit before 1995, a lot of astronomers had the idea of essentially surveying a bunch of stars that look like the sun in search of maybe evidence that there might be something massive enough of a mass similar to that of the planets in our solar system that would orbit them. And so what they discovered was what we call the hot Jupiter. So we're not very imaginative in exoplanets sometimes. A hot Jupiter essentially is just a planet that has a similar mass and a similar size as Jupiter. But instead of being located super far away from the sun, it's very, very close to its star. So 51 Pegasus B has a year or an orbital period of about 4 days. So instead of taking an entire year like the Earth does to do a full revolution around the sun, this hot Jupiter did a full revolution, a full journey in just 4 days. So this means that it's not only hot, it's being blasted with stellar radiation. And so really this discovery was revolutionary. I think it sent a lot of people to re-question the way we thought that planets form and evolve. And so a couple of years ago, the Nobel Prize in Physics was awarded to Michel Maillard and Didier Queloz for the discovery of 51 Pegasus. And really, since then, the field of exoplanet has exploded. And just recently, I think like 2 weeks ago, we have now achieved a total number of 6,000 exoplanets that have been discovered. Okay, so I guess there's two questions. The first is what? Why did it take so long? And also, how did we become so good? But inherently, finding an exoplanet is a very difficult measurement to make. The one reason is because they're small and they're far, but oftentimes they're also orbiting a star, which is very bright, and the brightness kind of like overwhelms the brightness of the planet. But because they're so far and so close to their host star, when we take a picture of them, I don't know if this is my next slide, I hope so. Okay. So let's imagine that this is what you're picturing when you're seeing a star and an exoplanet that's orbiting around. Because it's so close, sometimes it passes in front. The idea now, when you think of detecting them, hopefully you could take a picture and you could see the star and the sun and the planet sort of like separated. But in reality, for a long time, this is what the quality of our data was. So essentially we had 9 pixels worth of information. And essentially, the star and the planet are both falling onto the same pixel here, so we can't really tell them apart. So you can't use images to find planets here, but astronomers thought for a very long time, and they're like, there must be some influence that the planet has over the star that perhaps we can detect. So we're not seeing the planet directly, but if you can see the star doing something weird and periodically, then perhaps this could be associated with a planet orbiting it. So this is when one of the methods for finding exoplanets was launched, and this has been one of the most successful ones. So transiting methods. Essentially, when a planet passes in front of the star, it blocks a little bit of an incoming flux coming from the star. And so you suddenly see that the star is slightly dimmer momentarily until the planet passes away. And so here, you can imagine that the bigger the planet, the bigger the dip. So the bigger the portion of the star that is being blocked by the planet. But once you see a single dip, it doesn't mean that you have detected a planet. It basically means that you saw something passing in front. In order to make sure that you found a planet, and this is something that the Kepler and the TESS mission have done and is doing currently in very efficient way is to basically monitor a bunch of stars and wait for these dips to happen. But the key here is that we want to observe them for at least 3 times. And the reason being, if you see it once, it means that something is passing in front. If you see it twice, it means maybe 2 things are passing in front. It doesn't mean that they're necessarily correlated. But if you see it 3 times and that the spacing between how when these happen is constantly the same, it means that something is orbiting around it sort of periodically and giving the same signal here. So how deep these dips are tell you about the size of the planet, or not the size of the Earth, but the size of the planet here. And then the distance between, not the distance, but time interval between each of these dips tell you about the orbit of the planet. So if it does it again, then we have a very precise measurement of how often the planet is orbiting around the star. And this method has been widely successful, so successful that we found over thousands of exoplanets, and you can see them here. This is the first graph that I'm showing. So at the bottom here, you have orbital period, so how long it takes for the planets to orbit around the star. And then you have planetary mass over here. And so one thing that you can see here, and I've overplotted the planet of our solar system, is that a lot of the exoplanets that we have found are vastly different from the planet of the solar system here. But we found so many of them, and you can sort of see clumps here and there, that we started making categories of exoplanets here. So I'm just going to name a few. So up here, these were the very first that were discovered. You have the hot Jupiters. This is because they're large and they orbit around their star very frequently, so they were much easy to see. Then we have the cold giants. So these are planets that are as massive as Jupiter, but they just orbit on longer orbital periods. So we don't call them hot Jupiters, they're just cold giants. Finally, we have these type of planets here, where we call them water world. So they are planets that are sort of in between the size of Saturn and Uranus and Neptune. And we don't really know what they are. So we don't have them in our solar system, but one of the leading hypotheses is that they might be water-rich planets. So essentially, rocky planets that are covered with an ocean, a single ocean over the bed of rock. And then down here, these planets are smaller in mass. So we think that they're comparable to the terrestrial worlds of our solar system. But the ones that I'm going to talk about is this very extreme category of planets. So these, we call them ultra short period planets because they have ultra short periods. So essentially, they take only a few hours to do a complete journey around their star. And because, I'm going to pull out a quote here, because they are so extreme, one of the big questions is how the hell did they get there? So we know that planets form, and we have known for a long time now that planets don't form where they are found today. Most of the time they're formed somewhere, and there's something that can make them migrate within the planetary system as well. But all of this complex mechanism here, or all this complex evolution, is very difficult to pinpoint. So there's a lot of different physics and different processes that are happening at the same time. And in order to really study them, sometimes it's very useful to look at extreme cases because they're oftentimes the most revealing. And then another thing that I think is fun about lava planets is that they also allow you to study extreme atmospheric physics that we do not find in our solar system. So in a way, these exoplanets are labs that we do not have on Earth because we cannot just create an Earth 2.0 and decide to make it hotter. I hope we don't do that, actually. Okay, so because they're so close to their host star, we believe that they are what we call tidally locked. So when they're so close to the star, the gravitational interaction with the star will basically make it such that the orbital period of the planet is the same as the period of rotation of the planet. So if you see here on the left side, I have a tidally locked planet, and you can see that the smiley face is always facing the sun over here. And so what you have for these planets is that instead of experiencing the day and the night at any point on the planet, you basically have one hemisphere that is always illuminated by the star, and then the other, so the backside, that is never illuminated by the star. So a little bit like the moon and the Earth. So you have the side of the moon that is always facing the Earth, and you have the dark side of it. And so this gives you a very particular climate. So let's pretend that this is a real lava planet or a short period planet. So essentially you have one side that is blasted with stellar radiation. And in fact, it's so close that the temperature on the day side can get up to 3000 Kelvin or 3000 Celsius over here. On the night side, because there's nothing that's really heating up the planet, it can be as cold as 100 degrees. Doesn't seem very cold here, but it can be as cold as 100 degrees or even less, unless you have an atmosphere that could carry some heat from the day side to the night side. So here, when we talk about sunsets, is a little bit bizarre. So sunsets don't happen at a particular time, but rather they happen at a particular place. So instead of timing your sunset, you just have to travel in order to see a sunset on these planets. So that's pretty wild. Yeah. So essentially, instead of sunset and sunrise, you have a permanent dawn and dusk region. Okay. So next, we know how big the planets are, and most of them are rocky. So essentially, they have the size of the Earth or a little bit bigger sometimes. The next thing that we want to ask ourselves is how heavy are they? And there is one way of measuring this, again, without measuring it directly. So essentially, we're looking at the effect of the planet onto their star. So here, I'm going to introduce you, some of you might already know this concept, the concept of Doppler effect. So you might have experienced this multiple times in your life. Essentially, when you hear an ambulance, for example, passing you, as the ambulance is approaching you, you'll hear a higher pitch. And this is because the wave is sort of compressing as the ambulance is moving towards you. But when the ambulance is moving behind you, suddenly the pitch of the sound that you're going to hear is lower. And this is now because the waves are kind of like elongated as the object is moving away. The same concept happens with light as well. We just don't see it as well. Oops. But essentially, when you or anything that I'm looking at that is emitting light is moving towards me, then I'm not going to hear a higher pitch, but I'm going to see a higher pitch. What I mean by this is that suddenly the object is going to look a little bluer as it's approaching me. And then when the object is moving away from me, it's going to look redder. And again, because it has lower frequency. And so you can imagine that if you have a planet that is orbiting around you, it will periodically move towards you and away from you. And so essentially what we're doing now is, again, I'm telling you, we can't really see these planets. They're very, very faint. But when a planet orbits around a star, it doesn't really orbit around the star. What it orbits around is the common center of mass between the planet and the star. So you can see here that the planet is sort of like pulling on the star as well as it orbits around the star. That makes the star wobble periodically as the planet is orbiting around the star. And this is what these Nobelists had been trying to measure, essentially, is that they surveyed a bunch of stars and they tried to figure out what is the color of the star and what is the radial velocity. So is it moving towards me or away from me? And so in practice, this is what you're going to see. So this over here is what we call the spectrum of a star. And you can see these lines over here that are corresponding to different absorption lines. So it depends on what's happening on the composition of the atmosphere of the star. And you can see this like shift. So they kind of like shift periodically towards the blue and the red as the planet is orbiting around you. And this allows us to measure how much shifting there is. And the bigger the planet, the more massive the planet, the larger of a shift you'll see in this spectrum over here. And so people have done this for a bunch of stars. And whenever there's an exoplanet that is discovered throughout the transit method, we know the size of the planet, but we really want to know the density. You know, is it a ball of gas or is it a ball of rock? And so people are doing this. And for this, you don't need to go to space. You can use this from the ground here. And so a lot of telescopes from the ground are doing this periodically and have revealed that a lot of the ultra short period planets that we've seen actually have masses that are comparable to that of the Earth. So what I'm showing here is kind of like a summary of all of the rocky planets that we have found. So planets that are rocky in size-ish. And all of the points that you see over here are different planets. The colors of each of the planets represents how hot they are. So you can see that these ultra short period, because they're so close to their star, they're being blasted with heat. And on this plot here, they're represented by the yellowish color. And so you can see that all of the yellow points are kind of like down here on this line. So the different lines that you see on this plot here at the bottom, it basically means these planets are super dense. They are as dense as a ball of rock with a core of that. And as you move up in this plot over here, they become less and less dense. So essentially, their density gets lower enough that you need an atmosphere. You need something really light enveloping them in order to describe their density. So we know that these rocky worlds, or these ultra short period planets, are made of mainly rock. So if they're mainly made of rock and they're being blasted with stellar radiation, then you can imagine that the planet can be hot enough so that the day side of these planets can be molten. And so instead of having an ocean of water on them, you would have an ocean of magma that is there perpetually. But the thing is, the density doesn't tell you everything about a planet. There's still what we call the degeneracy. So essentially, we don't know from the same density, you can have a planet that has a substantial atmosphere and a very, very big, heavy core, or you can have a planet that has a tiny, tiny core and a tiny, tiny atmosphere. So we don't really know what we don't really know what could explain these planets unless you probe the atmosphere itself. So about detecting atmospheres, that's our next steps in order to bring these degeneracy, in order to really understand if we can have sunsets and rainbows and whatnot. You need to know how thick the atmosphere is and what's the makeup of this atmosphere. So to detect the atmospheres of exoplanets, one of the biggest or one of the most popular way of determining this and detecting them is through what we call transit spectroscopy or transmission spectroscopy. So as you can see here, as so you don't see the star here, but just pretend that there's a star over here that's sort of emitting light from this side. As the starlight is passing through the atmosphere, it will interfere and interact with the atmosphere itself. And you can sort of see them in the spectrum that you will measure in the end. So when you look at an exoplanet, you don't only look at the planet itself, but you look at the starlight mostly. And so if there is an atmosphere, there will be some interaction and signatures that you can detect. But if there isn't, then you won't detect anything. And so one way of seeing this, so we know the spectra of the stars very well. We've studied them for decades now. And so we know exactly what's the makeup of a lot of stars. And when the transit is happening, you'll see the planet is blocking some light, but it will also preferentially absorb some starlight at very specific wavelengths, at very specific color. And depending on the molecule, the spacing, so the different colors that will be absorbed will be different. Each molecule has its own kind of like barcode for in these spectra over here. And so to do these were measurements that were very difficult to make because for the longest time, we've never built anything that had the stability or the precision to measure this. But thankfully and successfully, back in 2021, the James Webb Space Telescope was launched and it really revolutionized our ability to now have these very precise measurements in order to determine whether or not there are atmospheres and what the makeup of atmospheres is on exoplanets. And so over here, I'm just highlighting one of the contribution of Canada here. So the James Webb Space Telescope is this big organization or this big project that involved not only NASA, but also the Canadian Space Agency and the European Space Agency. And one of the instruments on the James Webb Space Telescope was made specifically to try to detect these spectrum of exoplanets. The instrument itself is called MIRIS, and it was built out here in Canada with a major part also at the University of Montreal. So this is kind of like our local contribution. And so here I just wanted to show some images in case you haven't seen them. But this is the James Webb Space Telescope a few days before it launched. And so you can see here that this is a massive telescope. So the size of the mirror itself is about 6 meters. So this is like Yeah, so it's a pretty large telescope, and you can see little humans down here for scales. Because it's so big, it doesn't fit any of the rockets that we had to launch to space. And so really, in order to be able to launch them to space, we had to do some sort of like space origami and kind of pull them onto them in order for it to fit inside of the rocket and be launched. And this was launched successfully on Christmas of 2021. So this was a weird Christmas. It was in the middle of COVID, but at least we had something to rejoice about. And so we all gathered on Zoom and looked at the launch together. And so here, I'm just gonna show that basically different molecules have their own signature. So water has these like very particular features here. I'm not expecting you to remember them by heart. We have computers to kind of memorize this. And then silicate and magnesium also have their own. So this allows us to differentiate, is the signal that we are seeing coming from water, or is it coming from like weird exotic gases that we can see on Okay, so I've talked about these ultra short planets, and I've told you that they have a permanent day side and a permanent and a permanent night side. But one thing that's very particular here is we have a lot of questions about them. So we don't really know what they're made of, but we know that the atmosphere of these planets are not made of water, because any kind of water would evaporate already. But we think that perhaps the makeup of the atmosphere on these planets, because they're so dense, doesn't come from the atmosphere that they were born with, but rather the atmosphere that was outgassed in the future. So because they have this like open magma ocean on the day side, what does oceans on Earth do? They evaporate, and then we eventually get rain and clouds. And so you can ask yourself the same thing. Can these lava planets evaporate enough atmosphere, enough gases to build a full atmosphere? And if it does it get dense enough in order to condensate and then rain out? And if it does, can it remain in cloudy form, or are the winds too strong to blow them away, and so you don't have any clouds? So these are all questions that we don't know yet, but perhaps we can answer them with lava planet mapping, so exoplanet mapping, that I've talked to some people in the crowd earlier today. So what I'm trying to do here is, my dream is to be able to build kind of what we see, these like maps over here. So essentially, this is a map of the Earth with the background color over here represents a temperature at different location on the Earth. And then you see all of these arrows above that tells you where the winds are blowing and how strong the winds are blowing in different places. You might have seen this, and now I'm talking to a mixed crowd here, but for people who used to watch the Weather Channel, this is this is what I'm trying to do for exoplanets here. So I'm trying to predict what places are cold, what places are hot, where does it rain, and where does it not rain. Unfortunately, like I said, it's very difficult to take a picture of an exoplanet, so we have to be a little bit innovative in order to rebuild these maps and infer where does it rain, how strong are the winds, and etc. Okay, so the way that we do this on Earth is we have these satellites that are orbiting on Earth, and they're looking at different parts of Earth at all time. Unfortunately, the James Webb Space Telescope, we're not sending it out to orbiting around one exoplanet at a time. That would be too long. And also that would be too far in order for us to continue communicating with the James Webb Space Telescope. The James Webb Space Telescope is located in the solar system, but it's just looking outward. And so in order to really get a sense of the different parts of an exoplanet, we can't just turn around on the exoplanet. We have to wait for the exoplanet to show us different faces as it's rotating in space. So the way that we do this is by getting what we call a phase curve. So essentially, we stare at a planet for long enough for the planet to complete a full orbit around the star. And so you can see here that as the planet is passing in front of the star, you'll have a transit when the planet is blocking some light from the star. But momentarily, at some point, it will also be eclipsed behind the star. So there's also a moment where you don't see the light coming from the planet. And so that allows you to measure how bright the planet is. And if you look in the infrared, which is a part of the spectrum that gives you a sense of how hot something is, it can also give you the temperature or the exact temperature of the planet. So this is actually what the data that would look like. A lot of people are rejoiced whenever we tell them that we have JWST observations, but in reality, the images are not super interesting, and most of the time in order to tease out information, we have to aggregate them into something that looks like this. So here, what you see is the brightness of the star over time. And so in the middle here, you see this big dip. That's a transit. So that's when the planet is passing in front and blocking some part of the sky, part of the star. And then the two little dips that you see at the two ends here are the secondary eclipse. So this is the light that is missing when the planet is passing behind the star. And then finally, if you zoom in into this part, you also see that it's not a straight line between the eclipses. You see this kind of like modulation here. So essentially, as the planet is orbiting the star, you'll see different parts of the day and the night part of the sky. And that allows you to see this like modulation. So these like little variation in brightness here that is causing by the planet. And you can essentially take this curve and infer what part of the planet has to be very hot and what part of the planet has to be very cold. And so oftentimes, I don't know if you see it here, but the brightest spot on this is not really aligned with what we call longitude of 0. So that's the part that is receiving the most amount of light. It's a little shifted from this part. So it means that this planet must have had a lot of winds and a lot of strong winds in order to move the hottest spot of the planet to this size. And so this allows us to place constraint as to how strong the wind needs to be blowing in order to reproduce this map and the curve that we see here, that we saw earlier. And so here's the thing. If there is a hotspot shift, it means that there is an atmosphere. You must have some dynamics that is moving heat away, because normally your ocean, if it's only a day-side ocean, you won't have enough efficiency in how quickly heat is being moved. And so this is sort of like one of the indications that we can find atmospheres on it. And also this is done with the JWST, by the way. So we couldn't do this before. This is kind of like something that is a novelty over the past few years. Okay, so looking for atmosphere on lava planets is maybe not such a crazy idea. We think that these lava planets must have had an atmosphere, actually. So essentially, because you have this magma pool that is permanent on the base side, you always have outgas from the base side. But one way of distinguishing or finding out what composition you can have in the atmosphere is by looking at the night side as well. So the map that I showed you earlier not only covered the day side, but it went all the way to the back side as well. And the idea now is, so you can imagine that if the atmosphere didn't have any water or lighter molecules, so if it was only like silicate and the like rock vapor, rock condensates at a very high temperature. So I don't know if you've ever looked at lava. It needs to be very, very hot in order for it to be in the liquid form. It needs to be even hotter in order for it to be in gas form. And so as you move away from the substellar point, so essentially starlight is hitting from the top. As you move away from this substellar point here, things are going to start getting cooler because you don't have as much illumination. And then at some point, as you move away, it's going to become so cold that if the entirety of the atmosphere is made out of rock vapor, it's going to all condense out. And so on these planets, we're unsure whether or not the atmosphere is extending all the way to the night side, because if it collapses halfway through the night side, you're only getting a partial atmosphere on the day side. And then once you get on the other side, suddenly your atmosphere is less. It's kind of like an airless world. But if you have a lot of oxygen or a lot of nitrogen, so these are gases that doesn't condense at high temperature, then that would allow your atmosphere to go all the way to the night side. So going back to the phase curve over here, if you see any hints of a hot night side, that can tell you that you have an atmosphere, but not only that you have an atmosphere, it's probably an atmosphere that is made of lighter gases like oxygen or nitrogen. And so I think I'm going above the time now, but now we're just getting started. So we just got a few sets of new observations, including the ones that Kareem has started to talk about. And we can now determine our ability of being able to measure temperature at very precise, with a lot of precision, essentially, that eventually, as we build up more observations and more signal to noise, we can start asking ourselves, in the entire population of lava planets, what do the dawn and dusk skies look like? Is there any distortion made by the atmosphere, or is the atmosphere too opaque in order to see anything? And does it rain? And if it does rain, what does these droplets look like? And so we're now kind of bridging outside of astronomy here. A lot of our geologist friends are very excited about these things. They have never thought about having lava at such high temperature and high pressure that we now are collaborating with geophysicists and geochemists that are now reworking their lab in order to heat up a piece of rocks in order to really understand what the properties of these rocks are at these high temperature, so that we can better understand what these maps of exoplanets, of lava planets can look like. So I'm here, I didn't show a lot of results from the JWST here, but I just want to say that after this first round of JWST observations, this has really motivated and created a lot of collaboration with geophysicists here. And after a few rounds of trial, we are now have been successful, and we got 100 hours on the JWST last cycle to not only look at the atmosphere of these planets, but essentially to look at what does the interior of the planet look like. So if the planet doesn't have an atmosphere that extends all the way to the night side, then looking at the night side can tell you something about what's inside of the atmosphere, what's inside of the planet. So essentially, how big is the lava ocean? And then what does the night side look like? If you have condensate, so basically if things start to condensate on the night side, you can start building up a lot of minerals on the night side. So you can imagine that you can start having these like mountains of minerals building on the night side as well. So essentially what I'm ending the talk here now with is JWST is really revolutionizing our way of thinking about planets, but it's also now highlighting that we can use these planets to really understand cool and exotic geology that happens on planets in general. So with this, I'll stop here and see if there's any questions. Yeah. How do you want to proceed?
One of our local moons around Jupiter is very volcanic in nature, Io, of course, turning itself inside out practically.
Yeah.
As looking at that and what we can see with what it spews out, has that helped any of these models? And
yeah. Yes, so it has not only helped with these models, but it has helped motivating a lot of these observations as well. And so with the James Webb Space Telescope, we're able to probe a certain molecule that's called SO2. And SO2 has been discovered and detected on Io because of volcanic activity. So essentially from these volcanoes, you have a lot of outgassing that brings up these SO2 from the ground up. And so we're hoping that from our little survey of 5 lava planets, maybe one of them will show signs of SO2 over here. And then the other thing is a lot of these planets, I've talked about them being blasted with stellar radiation coming from the top. So essentially it's from the outside of the gas heated. Io is different. Io is heated from the inside. It has a lot of tidal heating due to Jupiter and its orbit. And so this is why you have these volcanoes as well. So we think that all lava planets, if you don't have internal heating, so basically if the underneath is cold, you would not have these volcanoes. But if you have planets that somehow have been able to retain some of the heat, or if they have some eccentricity in tidal heating as well, you might be able to see SO2. So this is kind of like the parallel that we're drawing between exoplanets and Io.
thank you.
Yes.
2 questions. One, I didn't quite understand how you're measuring the dark side of the planet, and I guess perhaps it's just temperature that you're able to guess from the dark side. I'm trying to figure this out. But my second question is, if there is condensation that then falls back on the planet, and it's always happening the same way because it's tidally locked, then will it stay spherical, and would you still call it a planet?
Yeah, and that's a very good question. So the first one, I can roll back the slides over here to this part. So essentially during secondary eclipses is when you see the day side. If you measure the entire thing, you'll see that around transit time is when you mostly see the night side. So essentially you see this curve over here. The level of emission that you see near transit is what tells you about is essentially light from the night side of the planet. So if there was no temperature, so basically if it was super cold, the line would hit the gray line that you see over here. So at some point you don't see much. So that's your first question about the night side. And then the other one, so if you perpetually have rain that is kind of like condensating and falling down on the night sky, at some point you can imagine that you're going to start having these like ginormous mountains, and they can start having similar masses to the planet itself. So you'll start being distorted. And so if you have a large mass in mountains, at some point it's going to be so heavy that it's going to be gravitational pull to the inside. So yes, you can have kind of like this distortion that will kind of restore. So some mass transfer happening here. Again, I think the information about the interior of the planet is very crucial here. So if your entire interior is molten, it'll be very easy for these like mountains to kind of like fall in. They're kind of like sink into the planet. If the interior is completely solid, then the mountains would start having a much harder time to kind of like sink into the planet. And so eventually you'll start having a distortion. I don't know whether or not this will be called a planet or not. For now, the distortion and the roundness of planet only applies to the planet of the solar system. For the planets outside of the solar system, there's too much uncertainty for us to be able to say, yes, this planet is round, and no, this planet is egg-shaped. Yes.
I'm more interested in your time on the James Webb Space Telescope. When did you start getting time on that?
Yeah.
What year?
So that's
and how does it work? And how far back are you lined up, and are you sharing with other people?
Yeah. So the James Webb Space Telescope has a what we call the way that it proceeds is through general observing requests. So essentially every year, because it's not a telescope that has a particular mission, it's a general purpose telescope that can be used for a lot of different science, including exoplanets, galaxies, black holes, and etc. The way that we do this is that every year there's a call. So NASA and the Space Telescope in Baltimore put out a call and they say, please tell us what you want to do, how much time you want, and what you would like to do with the James Webb Space Telescope, and how impactful you think this is. So basically, you write up a big document where you do your calculations to make sure that you'll be able to measure what you think you're going to measure. And then you try as convincingly as possible to convince the Space Telescope. Space Telescope is then not going to do it itself. It's going to invite experts all over the world to kind of gather for like a month long and read all of these proposals and discuss them and kind of like rank them and decide, all right, for this year, we have this amount of hours that we can allocate. And then these are the programs that are going to get. So normally it goes every year. And then at the end of the year, the cycle is going to restart. So for the first cycle, because James Webb was launched in 2021, actually it was delayed for a few times. I don't know when the first time you heard of the James Webb Space Telescope, but the first launch date was back in 2007. So it was delayed by a little bit more than a decade. And so at some point, we thought it was going to launch in 2020, and then it was delayed for another year, and that was partly because of COVID. So in the middle of COVID, at some point, we were all told that we had to put together these James Webb Space Telescope proposal. And so in November 2020, my partner can attest, I was awake for like maybe a week long trying to put together a proposal. And it was also a wonderful time in astronomy. It was a time where all of us had not seen any of our colleagues in person for a very long time. And so feeling kind of attached to anyone was a bit difficult. But for that month long leading to the James Webb deadline, we all gathered together and then Zoomed very frequently and all complained on Twitter at the same time. At some point, all of us were using this website called Overleaf. So this is a platform that allows us to write text together. And so many of us were working on Overleaf at the same time, it crashed. And so there was a panic mode maybe like three days before. But essentially, so we put in their proposal, and then a team of experts is gathered, and they have about 3 months to rank all the proposal and decide which are going to get time and not. And so about like in March of 2021 is when we found out we were going to have time. And the observations were not acquired until June of 2022. Because there's a lot of things in the sky, you have to be kind of like smart to make sure that you don't flip back and forth between different parts of the sky and be smart.
Well, thanks. We don't have, it's a very short list of people who've come and talked to us that have access to the Hubble Space Telescope.
Yeah, there's not a lot, but thankfully the launch was perfect. So essentially there was a lot of fuel for correcting the trajectory of JWST in case it didn't launch perfectly. But thankfully, it launched so perfectly that a minimal amount of fuel was used, meaning that there is now enough fuel for the James Webb Space Telescope to operate for 20 years. So for the Sept students in the room, perhaps maybe one day if you decide to become an astronomer, JWST is still going to be there for you to be able to get.
So I remember we watched the launch together online and the 400 plus points of failure over 6 months, you're holding your breath at every single one. It was after that that you actually, towards the last stage of the testing and everything that you found out.
Yes.
Up until then, what was your view of what James Webb would provide versus what you've actually seen it provide now that you're actually part of one set of the data collection teams?
Oh, I thought that we were just going to chase oddballs. So essentially, I thought that we were going to look for these like very peculiar objects and go, this is super interesting. We can go and look at this one. But I think as we looked at a lot of these observations, a lot more questions kept popping up. Or like there's like 5 different things that can explain what we're seeing here. But in order to really pinpoint which of the 5, we really need to observe kind of like a population. So one exoplanet might stand out from the rest, and you don't know whether or not it's a typical planet or a unique planet. In order to really find out, you need to look at several of them and kind of look for trends. None of the planets are identical twins. And so by comparing different planets, you can learn a lot more about each planet individually. And I think this is one thing that I didn't see the field going towards, is essentially asking for larger surveys, so being able to do these instead of like dedicated single mission, having like a very large survey. And I think this year is when we really saw that happening. So the program that I have with JWST is a 100-hour program because we're looking at a series of planets. But the other largest program that were approved this cycle was 250 hours at York University. So I think we're really privileged here in Canada that we have amazing scientists that were awarded a lot of time. So I think this is looking bright for the future of astronomy in Canada.
Is the time allocated, is it based on participants in the development of James Webb, or is it equally open to across the world?
So the one that I'm talking about is equally open to the world. But for the first cycle, it's true that there was some time, sort of guaranteed time, that was allocated for people who contributed directly to the instruments in the telescope. So for example, the University of Montreal and the team in Canada were awarded something like 200 to 400 hours of time on the James Webb that were split between galaxies and exoplanets. So not only we got these extra programs by me as a student at the time and other students as well, but we also had this guaranteed time that also expanded a lot of the exoplanet research that we've done.
So when you mentioned that there are atmospheres on some of these lab, I was like really surprised. And the reason why I was surprised is because you were saying that they're really close to their stars, and the solar radiation from these stars must be really intense on these planets. So does that mean that we can say that if the data planets that are really close to their stars have an atmosphere, does that mean that they must have a molten iron core to make a really strong geomagnetic field around them to keep that atmosphere in? Is that true, or is that way off? Or
yeah, that's a very good train of thought. So essentially, because they're so close to their host star, it's true that they experience a lot of radiation. So you can expect their atmosphere to be blown away. And this is the case for a lot of rocks, for a lot of planets that we found. For a lot of planets, it's sort of different. It's because they're so hot that they have this open magma ocean that's constantly evaporating, that's sort of replenishing this atmosphere. So even though it's being blown away all the time, all of the lighter elements are gone, but we can sort of think that like this open magma ocean will continue to replenish it. Although I'll give a scoop now because it's on the internet, but the press release is not out yet. So look, stay tuned for a press release next week. But we actually found a lava planet that had a substantial amount of atmosphere. So that was very surprising for us. We generally don't think that they can have molecule that's like a CO2 or even water. But this planet seems to have evidence that it could be there could be a lot of lighter elements. So one of the leading hypotheses is perhaps there's something happening in the interior of the planet. Maybe you have this iron core, a liquid iron core, that's generating a large magnetic field that's sort of like shielding the atmosphere away from this strong irradiation from the star. So again, all of these are open questions for which we don't really have answers now. And I think we're just only starting to have data to have empirical answers.
We're gonna take one of the questions from online. Fiza's gonna offer the question for us.
So this question is by Lyndon Neal that asks, as biosignatures of life on rocks have been discovered on Mars by the Perseverance rover, what do you think they would look like on exoplanets? Realize they may not be carbon-based.
Yeah, so that's a very good question. The way that they would look like on the exoplanets is very similar to what you would expect. Not on Mars because we don't have the ability of sending a rover on exoplanet and finding weird molecules or weird traces on rocket, but they would be in vapor form. So essentially what we're looking for are biosignatures or essentially molecules that we don't expect to find in an atmosphere. One of the examples on Earth, for example, is ozone and methane. So both of them surviving on Earth at the same time is very weird because chemically they will kind of like combine and create a lot of CO2 instead. But the fact that they're operating and existing at the same time is because us humans and animals are living here and producing them simultaneously. So what we're looking for are gases and atmospheres that we don't expect to be there unless there is some kind of form of life. But it's true that the only form of life that we know of is the life that we have on Earth here. So again, I think it takes a lot of lab experiments, for example, to recreate atmospheres or exotic atmosphere that we might not have on Earth to really understand what are the chemical properties of these weird atmospheres. And then is there any molecules that we don't expect to see on such atmosphere? So now that we have thousands of exoplanets with different sizes and different properties, we can start recreating some of these properties in the lab to understand what is expected normally. And then if we find something odd and we can not replicate it in the lab, and that might be a sign of not necessarily a biosignature, just a disruptor, but it's perhaps in the long run, we will be able to determine that there are smoking gun evidence that can be tied to life and others that can just be tied to weird things like plate tectonics or weird activities on the planet.
Got a question? Oh, I did, yeah. So if the scenario you talked about made me think, would there be auroras?
Yes,
Yeah.
that's a very good question. So Jupiter has auroras. HSC has been able to discover them now. So yes, we can imagine that perhaps we can have auroras, especially if there's a magnetic pole. And the way that we detect them yet, so we think that we can detect auroras via radio emission. So they would be not detected with the James Webb Space Telescope, for example, but there are researchers currently that are using radio telescope to kind of survey the sky to look for potential signs of it. It has been not super successful so far. It doesn't mean that there is none. I think it's just that the signals are too small for us to do that. Yes.
So speaking of radio emissions, and I keep looking at this particular slide here, and I wonder whether James Webb Telescope is able to detect black body radiation from the dark side of the planet, and whether that would tell us anything about the dark side, or at least measure temperature.
Yes. Yes, so we can. So just like looking at the slide over here, basically when you're looking at the dark side, so right around transit, essentially what you're seeing is emission. We don't know whether it's black body. There might be some molecules that are absorbing some light here, but basically what you're looking at is the emission from the night side.
And what that would tell you specifically about the dark side of the planet.
Yeah, so it tells us about the temperature of the dark side. And then because when we were looking at this, and I'm not showing this very well, so this looks like a photometric phase curve, but essentially what we get is a spectrum. So not only can we measure whether it looks like a black body, but if it doesn't look like a black body, so if there's our dips or kind of like features, we can also tie them to a specific molecule. So we can not only tell the temperature, but what kind of molecule you find on the night side. It's just that it's not a lot of light. It's still like a very, very small signal. We can't really do these for these lava planets yet, but hot Jupiters are amazing labs for this. So we've started detecting very molecules at very good constraints on these gas giants. Yes.
I know that Earth used to be somewhat a lava planet in its early stages. What are the odds that some of these planets could be like another Earth?
Yeah, that's a
Just
very
just like Earth.
Yeah, that's a very, very good question. Actually, this is why a lot of Earth scientists are interested in these lava planets. So you're completely right. All planets, including all terrestrial planets, including the Earth, started as a fully molten planet. And so because we can't really rewind back in time and figure out what has happened 4 billion years ago, and we're also very blind to what happened at the very early stages of the early Earth, we think that maybe studying these lava planets is going to tell us something about our own Earth. Yeah. So thank you for that question.
Carl, you had a question? Are you studying any particular type of sun or just what's out there? Yellow, blue, red?
Yeah.
Green?
That's a very good question. So at first we didn't care. I think in the early stages, we didn't care what star it orbited around. And then now in this larger survey, we're actually having a larger sample with different stars from different lava planets. So lava planets don't form around a preferential type of star. They kind of form around all types of stars. And so now we can sort of tease out, is there any relation between the atmosphere and the interior of the planet and the star itself? So perhaps stars that have higher metallicity, so higher amounts of metals, for example, can yield a very different light. This is to be found.
Sorry, is it possible we're talking about convection of molten metal and so on? So the dynamics, would that throw off the likelihood that it was tidally locked because it would be constantly changing depending on mass? Would that be, it's not something else other than that?
Yeah.
Yeah.
Yes. So again, the tidal lockedness, so the fact that the planet is tidally locked is something that we assume. So this is purely based on how close the planet is to the star and approximately the age of the star. We know how we can estimate from theory how long it's going to take for a planet to be tidally locked. But it's true that in the scenario where we start piling up mass on one side, it can kind of like break the planet away from tidal lockness. And this is something that we would be able to see here from observing a phase curve. So the reason why you have this kind of like a peak around the eclipses and your trough at transit is because you have tidal lockness. So you essentially have a configuration where only one side is illuminated. So this is why you have these like large temperature difference between the day side and the night side. If your planet was not tidally locked, it means that every side of your planet would be illuminated because it's sort of rotating. So you wouldn't have this large of an amplitude again. So your curve might look like something like the Earth, where you have a lot of wiggles instead of a single wiggle. So by observing, with our upcoming observations, we might be able to tell whether or not all of the planets are tidally locked, or if there are any exceptions where you might not have any tidal locks.
So before we just move off into informal discussion, given the number of students here and online from secondary, Sept, university, and very recent graduates, and you said you came through the system here, you went through Dawson, went to University of Montreal. What are your advice? How do you find your passion? How hard was it to move forward in astrophysics and astronomy and actually be able to go through all the way to the point now where you're a professor with your own research program?
Yeah, that's a very good idea. That's a very good question. I think for me, things kind of happened out of circumstances. So I always liked astronomy and astrophysics, or not that I've always liked it. I think I've only found out when I was in Sept and I took this Nadim's course. I decided to go into physics without really thinking that I would end up being an astronomer. I was still thinking that I would be a physics professor. And
You're welcome to it anytime you want.
like, I'll take you up on it maybe one day. But for me, I think what really helped me, and I think this might be counterintuitive, is I've chosen this path. I wasn't desperate to be an astronomer. I've always had interest outside, and kind of like reminding myself that astronomy was not the only thing. That I have multiple interests, and this is the one that I'm choosing, is also very great. I've also learned a lot from doing other things than exoplanets. So organizing hackathons, being interested in finance and other things as well, kind of gave me a lot of perspective as to how people work and how I can bring these work ethics or work framework into the work that I'm doing today. And so a lot of, and I don't know if you can tell, but I love talking and science communication as well. And so I think that also helped a lot in reminding myself and reigniting this passion that I have. Sometimes I get more excited to talk about my science, and then I go back and I'm more excited about doing my science. So for this, thank you for the invite, Karim.
Let's give it up to Karen. Well, I'm going to call on our center president, Maury, to give a thank you and to talk a little bit about some of the materials here. Maury?
I just want to thank you so much for your talk. Your excitement is infectious. You talk about different, I don't know, disciplines that you bring in, and we were talking before. My background's in cartography mapping, and I'm listening to this, and my voice is going, how can I map this to make it understandable to someone like myself who's not a scientist, but thinks visually? And I don't know, I might send you an email and ask for some data to play with. We'll be fun. So I want to thank you, but first, before I get into the fun stuff, this is fun. We have a table here. This is our goodie table, and everybody's welcome to come and take it. We have some planispheres, star finders. When the conditions are right and there's no clouds, we could use these. But when we go to events, people say, are the clouds out there? I go, clouds are always out there. They're just not sometimes visible. They're hiding, but they're there. So when they're there, take one of these and you can look up in the sky. We have some moon guides here, very basic one, but you could take your pair of binoculars. We had to talk about someone with binoculars. Just let me ask you, who here has binoculars at home? Wow. Okay, everybody's could be a potential astronomer. You haven't gone up there. Grab your binoculars. I don't care if they're the little green things that you use when you go camping, because I got one of those. They're nice and light, they hold them steady. Or those really giant ones that you have to have tripods and all sorts of things to hold it. Take your binoculars, point it to the moon, point it to a star, and just be amazed at what you can see with a simple thing that you have at home. In fact, we tell you, if you want to join us, don't buy a telescope right away. Wait a year or two. We love sharing our telescopes with everybody. We're a very friendly group. We love to talk about astronomy and other things and all our interests. Astronomy has many interests, from astrophotography to the moon. We have, first, our moon expert is somewhere there. Yes, there he is. We have people that do deep sky imaging that takes hours and hours on the computer. I don't like doing that. We have people that take pictures of this wide field of view landscapes that involve astronomy. And there's so many different things you can do with astronomy. So grab this, grab your binoculars, you get out there. No excuses, just out your front door. Don't have to go anywhere. Now, do you like what you heard and are excited? We have an event coming up next weekend. Come out there, it's going to be really different. Poetry and live music in the field out there. And it's going to be beautiful weather, clear skies, I guarantee it. I'm calling in all my favors in the free sky.
Remember, he guarantees it.
That's right. To help the guarantee, we like some elevations. To help them bring me in, yes, here. We have some goodies over here. We have some more over there. All these things take a little bit of a help. So help us bring it on. Now, for our speaker, we have a few little things for your office. Just a little memento.
Oh.
While you're doing your research and then late at night, what fuels an astronomer is coffee or tea, hot chocolate, eat them up. Bring the friends together under the stars.
Incredible.
Thank you so much. Thanks for joining us, everybody.
And if you're going to be sticking around for a little bit, we'll have any questions, want to talk a little more. We have coffee, we have some juice, we might have some more snacks in the room around the corner. Please help yourself so we don't have to take it home. Thank you again.
Thank you, everyone.